I'm Ziyan, and in this talk I'm pleased to present a recent work done with my colleagues Li Sun, Thomas Koenig, and Yasin Hishek on building a dataset for autonomous driving. The background of this work is the rapid development of autonomous driving in both academia and industry, driven by more and more powerful and advanced software and hardware, as well as the need of the development of human society, while the latter includes for the purposes of driver safety, efficiency, and low cost. The motivation behind our efforts is a requirement for effective perception and localization of autonomous vehicles, which mostly relies on the hardware and the software utilized. However, faced with a variety of hardware and software, people might feel overwhelmed, and cannot help wondering what makes a meaningful combination. For the former, knowing that there is no almighty and perfect sensor so far, and they all have limitations and edge cases. For example, the GNSS is extremely easy to navigate and works in all weather conditions, but its update frequency and accuracy are usually not enough to meet the requirements of autonomous driving. The LiDAR is generally very accurate and has a large field of view, but the representation of the sensory data is a set of sparse point clouds without easy-to-learn texture features. The camera can provide rich semantic and texture information, but their performance is subject to lighting conditions. In terms of software, an integrated system to properly and efficiently gather and process data from different sensors is envisaged. Different solutions are available as open source or closed source, for free or for profit. On the other hand, from the point of view of the robotics domain, what would be an easy-to-use, easy-to-share, and scalable dataset? In order to meet the aforementioned challenges, we developed a perception platform for autonomous driving with up to 11 sensors. In addition to considering the multimodality and the cost of the sensors used, we also focused on maximizing the visual scope and the sensor redundancy. It is worth noting that the fact that we have installed 11 sensors does not mean that this is our recommended solution, but rather to explore the possibilities of various combinations by making more devices available. In terms of software, we adopt the de facto standard system in robotics, namely ROS1. We agree that ROS1 is not suitable for autonomous driving, but ROS2 is. Since the latter is under active development, we hope that our work can give some reference to related work based on it. Leveraging the developed multi-sensor platform, we collected some data in the urban and suburban areas of Montpellier City in France, and make it into a dataset publicly available to the community. This dataset is full of challenges such as highly dynamic environments, sloping road, construction bypass, aggressive driving, etc. And since we captured the changes within a week and across seasons, it is particularly suitable for long-term autonomy research. Furthermore, we also collected data on roundabouts that are very common in France. At the end, based on the dataset, we provided a few easy-to-run baselines, a detailed comparison with other datasets, and the lessons learned building the platform. Our hardware platform is shown on the right, including two Velodyne 32-layer LiDARs installed side by side on the roof of the car, an IBO-Lux 4-layer LiDAR installed in the middle of the front bumper, a SIG-2 LiDAR and a Continental long-range radar mounted on the left part of the front bumper, two stereo cameras on the front and rear of the roof, two fisheye cameras on both sides of the middle of the roof, and finally, a GNSS receiver and an IMU placed in the trunk of the car. Here is a figure which is supposed to help us have an intuitive understanding of the previously mentioned visual scope and sensing redundancy. As you can see, the idea of the side-by-side placed Velodyne LiDARs is to reduce blind spots and enhance the point cloud of especially overlapping scanning areas. Also, the complementary perception of LiDAR and the camera is what we expected, and this therefore motivated us to have the forward-facing and the rear-facing stereo cameras, as well as two lateral-facing fisheye cameras. The combination use of the radar and the 4-layer LiDAR was designed to detect and track objects in front of the car more robustly, so as to strengthen driver safety. Finally, the view angle of the tilted LiDAR is tilted toward the ground to obtain road marking and boundary data. As we mentioned earlier, the software system is purely based on ROS1, and we managed to connect all devices to a single PC. The idea behind this practice is to avoid data out of sync caused by using multiple machines to receive and process data. Therefore, it allows us to obtain synchronized data at the software level, that is, timestamped by ROS. Moreover, the two Velodyne LiDARs each have a GPS receiver, and we obtain the hardware synchronization of the point cloud data through the PPA signal of the satellite. Besides, the ROS launch file we provide allows users to remove any spurious data due to blockage or reflections from the opposing LiDAR sensor. We also calibrated the extrinsic parameters of each camera using the ROS camera calibration package, while the LiDARs and IMU are with the factory intrinsic parameters. Part of the extrinsic calibration were done manually, but we admit that there is still room for improvement and recommend users to perform online calibration by themselves. The dataset we released mainly includes two parts. The first part is long-term data, which contains 11 collection rounds across 3 seasons, day and night, and a whole week. The length of the data recording is about 5 kilometers each round, and the routes pass through the city center, a park, a residential area, a commercial area, 2 bridges, and including a small and a big road loop for loop closure purpose. The vehicle position ground truth is provided by the GPS RTK system. Second part is the roundabout data. France has the largest number of roundabouts in the world, accounting for half of the world's total. This road form challenges both human driving and autonomous driving. In order to provide more data support for related research, we collected 10 roundabout data within 0.75 square kilometers, while these roundabouts come in various forms and sizes. With highly dynamic traffic, we conducted 2 data collection rounds on both cloudy and sunny days, and drove a full cycle for each roundabout. To sum it up, our dataset captures different weather conditions, road types, traffic conditions, temporal spatial changes, and various semantic scenarios. The dataset, baselines, and the related developments download addresses can be found on this slide. Or it is more convenient to just scan the QR code that appears on each slide. Although image data is already available, part of the image data is available and the other part is still being anonymized. This is in accordance with the latest European privacy law that requires us to obscure human faces and license plates. Finally, we are sorry for the delay in data processing due to the impact of the epidemic. The community has a consensus on the importance of data-driven research. The existing datasets are rich and diverse. The Kitty dataset must be one of the most famous datasets, which was collected using the Anyway platform, which contains a 64-layer city LiDAR, 2 grayscale cameras, and 2 color cameras, as well as a GPS IMU RTK system for vehicle position ground truth. Oxford Robocar dataset is a pioneering long-term dataset for autonomous driving, covering over 1 year and 1,000 kilometers of total distance, collected in Oxford with the famous Robocar platform. The data collection captured a wide range of variation, including illumination, weather, seasonal changes, roadworks, and building construction. The Robocar position ground truth is also provided by a GPS IMU RTK system. CAST dataset focuses on complex urban environments such as downtown area, apartment complexes, and underground parking lot. And the data collection was performed with a vehicle equipped with 13 sensors. In addition, some datasets including Apollo Escape, New Science, and Waymo, backed by industry, provide us with automotive-grade data. And finally, the recently released Canadian Advanced Driving Conditions Dataset made us feel the challenges of autonomous driving in Canada. Moreover, as our dataset is purely based on ROS, other ROS-based software for autonomous driving are worth to be mentioned, such as AutoWare, Apollo, and Udacity. I hope you enjoyed this talk, and for more information, please check out our paper. Thanks for listening.